Hi everyone. In this video, I'm going to explain about direct mapping. It is one of the major mapping function. So it's the simplest mapping function. Okay. So what is mapping function? In the previous video, I explained what is mapping. So mapping means we need to mention. See how we are having what main memory. So main memory is larger when compared to the cache memory. Whenever our processor wants to execute anything, first processor checks in the cache memory whether that statement or instruction is there here or not. If it is there here, it is called cache hit. It will take from here only, it will execute. Suppose CPU not find that instruction in the cache, then it is called cache miss. At that time, processor has to go to the main memory, bring that instruction, keep it in the cache, and then executes. Okay, this is the procedure. Now, since main memory is having many locations, too much of locations when compared to this one, this will have very less. Okay, so we need to find out which block of the main memory is brought into the which block of the cache. That we need to map. Okay, so for that we are using one mapping function is the direct mapping. Okay, now for that let us take, I told many times, so our main memory is divided into blocks. Okay, let it is divided into some blocks. Now one block, okay, then similarly, so now we have decided one block we are having what? For example, some n number of words. It may be anything. So in one block we can have 2 words, 4 words, 8 words, 16 words, that depends. Okay, so generally in one block contain multiple words. Okay, now whatever the block size of main memory, similarly again cache is also divided into blocks, and block size of cache should be same of block size of main memory. Okay, that means both block size should be same. Block size is same. Whatever the block size of main memory is same as the block size of cache memory. Okay, so now generally actually in technically, so here I'm using the block in both the time. Okay, but actually we'll call the blocks of main memory is called as pages, and blocks of cache memory is called as in frames. Generally that is the thing. Okay, blocks of cache is called frame and blocks of main memory is called pages. So the point is, whenever you are bringing page, that is one block, one page, from that it should be able to fit in that frame. Hence, the size of both the blocks of main memory and cache should be same. That means frame and page size should be same. So, but now I am using the word blocks only. Okay. So now each block contains some n number of words. In one block, n number of words. Okay. Now let us take in my example. So one block contains 16 words. Let us take this example. One block contains 16 words. And the next. Now, cache consists 128 blocks. How many blocks are there here? Cache contains 128 blocks. Okay. So now that I'm going to write down. Okay. So now if I'm write 128 blocks. Okay. 1, 2, 3 like that. So I'm having 128. So this is my block 0, block 1, block 2, like that. Last is 127. 0 to 127, totally 128 block. This is my cache. And in one block I'm having what? 4 words, 16 words. In one block, 16 words. Each block 16 words means 128 blocks into what? 128 blocks into 16 words. So how much? See, 10 blocks in one box 16, so total 160. Similarly, 128 blocks into 16 words. Okay, 128 into 16. How much we'll get? See, 128 into 16. So I'll get 2048. So that means 2048 words totally. So this I will call it as 2K words. 2K words. Okay. Next. So this is about what? Cache memory. Now, we know that our main memory is huge. Okay, so our main memory. Okay, again, main memory is also divided into what? Blocks. Now, how many blocks will be there in the main memory? Now, let us take in my example. So, this is my main memory. Main memory contains 4096 blocks. Again, in one block, 4096 blocks. So, this is my 0th block, 1, 2, 3. Let us say, for example, this is block 128. Block 128. See that I am writing here inside. Okay, inside this. Okay, writing. Okay, this is my block 0, 1, 2, 3. This is 128 block. Let us take this is 256 block. Let us take this is 384. This is 512. Last one is 4095. Totally 4096 blocks. So in each block 16 words. So into 16 words. So I will get 65,536 words. So this is nothing but 64k words. Okay, this means, okay, this is generally I am taking for this example. Now this is my block numbers. Similarly, this is my what block numbers. So again, this is block number 0, 1, 2. Last block is 127. Now I need to find out which block of this main memory should be stored in which one and how to find out that. Okay, that is the main thing. So because since 64k number of words are there, we have 64k different addresses. 64k addresses. So 64k addresses. 64k addresses means this is a 2 to the power of 16. That means we need 16 address lines. That means address bus. Address bus is 16 lines, 16 bit address. That means whenever our processor generates the address, it will generate 16-bit address, and always CPU generates the main memory address, this address. That means each one word is having some 16-bit addresses. That 16-bit addresses, now suppose always our processor generates what? Main memory address, 16-bit address in this example. Okay, but first it will check in where? Main memory address. But main memory is having how much? Only 128. Only 128. So but in 128 what we need? Only 7. Okay, so that means only 7-bit. So how to match this 16-bit with the 7-bit? That is the question. That is the challenge. Okay, that will be done very easily. So in direct mapping, what it will say is we always place what? Block J of main memory is stored in okay, block J modulus 128 of cache. That means always, this is the formula. Block J of main memory is placed in modulus 128 of cache block. Okay, for example, let's take one example now. For example, 128 block. Now here I need to move this 128 block. Where to move that 128 block? 120, see block 128 of main memory. So this 128 modulus 128. So modulus means remainder. Divide the number and take the remainder. 128 by 120 remainder is what? 0. That means in block 0, I am going to move this one here. 128 block. Suppose assume I want to move 513. 513 I want. So 513 means again 513 of main memory. See 513 is this one. Okay, 513 block. Now this block I want to move. 513 block 513 of main memory. That way 513 modulus 128. So I'll get remainder 1. That means block 1 of cache. That means this should be stored in block 1. So like that. So whatever the block of main memory, that block number you divide by 120 and take the remainder. In that block I need to round. So this is something like round robin fashion actually. Okay. So if you not leave that one, so that if you understand this concept is fine. Okay. So now in direct mapping, always we are moving some block J of main memory is moved to J modulus 128 of cache block. We move this one. Now, how to identify that one as it is present or not? Now, assume I moved here. Now, after moving here what I am having? Here block 128 I am having. Okay, 128 I am having. Here 513 I'm having here. Okay, so like that I'm having. Now I see. Now I have to check whether it is there or not, cache hit or not. So for that what we will do, now let me write some table. See, I have done this table. See, that I did because here, if you see here how many blocks I am having in the cache? Totally 128. 0, 1, 2, 3, 4, directly up to 127. So I written this one. That's what round robin. See, I written here 0 block, 1 block, 2 block, 3 block, like that. After 127 over what? Again, it will be 128, 129, 128, 129, 130, like that up to 255. Again next what? 256, 257 like this. This is what I told round robin. So now, see, this is like that. I have done 0 to 127, totally here 128. Again next 128, 129, 130. Again here 128, 255. Like that, you see, keep adding 0. Plus 128, plus 128, plus 128. Like this will keep. So last column is 396. Similarly, 1 plus 128, 129, plus 128, 257, plus 128, like that. So now written like this. Now totally, after writing this one, so totally I written up to 4095. So now this is my block numbers actually. So this I will call as a 0, 1, 2, 3, like that. This is the last 31. So totally will get how much? 32. Totally will get 32. Okay. Now I will tell why I have written all these things. I will tell you. Okay. Now, for example, assume now I want to bring some numbers. Okay. Some block of the what? Main memory. Okay. So now assume this is my cache memory. So cache memory consists of 128 blocks. So now I'm writing that 128 blocks. So this is my block 0, block 1, block 2. So let us take for example some block number later, right? So this is 127. So totally 128 blocks later. See whatever I'm doing tag. That means one tag number is associated with every block. See how we are getting a tag in our close whenever we take by right. So like some the price tag, whatever. So like that, every cache block is having one tag. Okay, that's also tag. So totally, how many blocks will get? 132, 32, 0 to 32. So that 32 is block the tags. Okay, that block tag number right in this here 0 to 31. The tag in this example. Okay. So now assume I want to bring 386. Okay, 386 block. Right. This memory block 386 I want to brought to here. So where to brought? No, 386 percentage 128. What is the remainder? I will get the remainder 2. That means now you bring block what? Block 386 of main memory 386 in block 2 of cache. Now 386 belongs to which one? 3. So my tag number is here 3 here. This is my tag number 3. Tag number 3. Okay. This is done. Now, whenever I brought, for assume I want to bring this block now. I want to bring this 4095 percentage 128. What is the remainder? I will get remainder 127. 127 is, so that block 4095 of main memory, I need to brought to where? So block 127 cache. So this is here 4095 block I brought here. Okay. Now this belongs to which one? 31. So the tag of this one is what? 31. Okay. Now similarly, let us take block 380. Now I want to bring 256. So 256 block of main memory. Where to block? 256 percentage 128. Remainder is 0. That means 256 I need to bring to what? Bring to block 0 of cache. So that 256 belongs to what? Tag number 2. So here the tag number is 2. Like that I got. Now, hope you understood up to here. Now assume our processor wants to take some instruction. It wants to execute some instruction. Now, first it will check it where? First it will check in the cache memory. So now it is just to check whether this there in the cache memory or not. But we know that what is how many bit address memory line, because in memory I am having 4096 blocks, in each block 16 words. So I am having 64K, that is equal to 16 bit address. 16 bit address address. Okay, that means now assume it will generate 16-bit address. For example, okay, for example, say, okay, this one, then suppose our processor generates 16-bit address. So let's say 0011 2 3 4 5 6 7, and then it generates, say, for example, 0101. Okay, for example. Okay, now this is 16-bit address. Now this is the 16-bit address processor generates to access the content which is there in the main memory, but it will check in the cache memory. Now, so how this address is used to identify the main memory block in this cache block? So let us see that one. So now, in cache memory, how many blocks I am having? Totally 128. In cache, we are having 128 blocks. So 128 is equal to 2 to the power of what? Okay, 2 to the power of question mark. What is equal to 128? So 2 to the power of 7 is equal to 128. So I need 7 bits. I need 7 number of bits to identify block number of cache. Okay, block number of cache. And then in each block, I'm having how much? 16 words. In one block, 16 words. So 16 is equal to 2 to the power of what? So 2 to the power of 4 is equal to 16. So 4 bit I need to identify which word. Okay, in block, that is in one block, see, in each block I'm writing separately. So in one block I'm having like 16 words. So in here, which words? Okay, that is also called as offset. That means in this, from the starting word, it may be 0, 1, 2, 3, 4, 5, 6, 7, 8, 9, 10, 11, 12, 13, 14, 15, 16. So which word? See, instruction is there. So to find out within the block, out of 16 words, which word contains our sentence or statement, to find out I need 4 bits. Okay, I need 4 bits for that. So now, but each block, see, out of 32 blocks, see, block 0, block 128, block 256. See, 128 modulus 128 0, 256 modulus 128 0, 384 modulus 128 0, like the 3968 modulus 128 0. So like that, so you get 32 different blocks. Out of these 32 blocks, any one block can come and sit in block 0. Okay, according to this formula. Similarly, any one of these blocks, any one of these 32 blocks can come and sit in block 1. Any one of these blocks can come and sit in the block number 2. So, totally my possibility is what? 32. So, the 32 will be written as a tag number. So, the higher are, okay, so now always the least one, okay, least 4 bits. The least 4 bits are used to identify the word within the block. That means in one block 16 words are there. Out of 16 words, which word contain our instruction? So to identify, we are using this least significant 4 bits. Okay, to identify the word. Next. So now I'm having 128 blocks in cache. To identify which block, cache block contains the main memory block, for that I'm using this 7 bits. Okay, that is next 7 bits. 3, 4, 5, 6, 7. Okay, now these 7 bits are used to identify the cache block. That means out of 128 blocks, which block contains? So we are using these 7 bits. Next remaining these 5 bits are used to identify the tag. Okay, this tag indicates the tag. That means because why 5 bits only? Because I need 32 different. Okay, 32 different groups. 2 to the power of what is equal to 32? 2 to the power of 5 is equal to 32. So I need 5 bits. So 5 bits. So in general, so my cache memory is divided into like this. Okay. So this is for the word, this is for the cache block, and this is for the tag. Okay. So this is for 4 bits, this is for 7 bits, for this tag is for 5 bits. So totally 5 plus 7, 12, 12 plus 4, 16. Totally 16-bit address. This is how, even though it is having only 128 blocks, even it is having 4096 blocks, this 16-bit address can be utilized to identify the 7-bit cache address. This is how it will map. Okay. For example, let us say, now I take the example. Okay, now I want to bring this block. I want to execute this statement 386. Assume one statement is there in this block, so I want to execute that. That means first CPU checks in where? CPU checks in the cache. Whether it is present is at 386. No, 386 belongs to which group? 3. The tag. The 3 is there, is 3 tag is there. It matches. This matches. So that means the cache is there. That is cache hit. Now the 386 block is present in the 2, okay, cache 2, okay, so that is 2, cache block 2, okay, so that is how it will identify, okay. So in this case 2 means now address is not here. See, I am not just randomly taken, so this address is what now cache block 2 means now it is 1 2 3 4 5 6 7. Now this is the cache block. Now cache block is 2. The 2 item in this array. Okay. Now this is what decimal equivalent is what 5. That means in this block 16 words. That means fifth word. That means 0 1 2 3 4 fifth. That word contains this statement. This is how it will match us. Okay, direct. Okay, this is how direct mapping. So summary is in direct mapping we are identifying which block of the main memory is brought into the which cache block. We are using this formula. So we just divide the memory block number by 128. That is one here in this 128. Suppose cache contains 256 divided by 256. So cache contains 64 divided by 64. Like that, size of the cache divided by and take the modulus. In that module, that block you have to place a module block. Okay, main memory block. Now, in order to identify, so the cache address, we are dividing the 16-bit address into like this, the least 4-bit for the word to identify which word, and this next 7 bits is used to identify which cache block number, and last 5 bits is to identify the tags. So that tags I explained like this. Okay, hope it understood very easy. Now, what is the advantage? So advantage is here, it is fixed. We know that any one of these blocks 0, 128, 253, 84 up to 316, totally any one of these 32 blocks should be brought into block 0 only, nowhere else. Similarly, any one of these 32 blocks should be brought into the block 1 of the cache, nowhere else. Okay, suppose, assume, right now I brought this 256, right now 256 block I brought into cache 0, okay, cache 0. Now, assume I want to bring next 384 also. Assume after some time I want to this one 384. Now, 384 divided by 128 also 0. That means that also I should be here only. But already it is having. So, what to do? So, simply you have to know, there is no any other possibility. I need to fix here only. That means here only I am overturn. I remove this 256, bring 384 here only. Okay, 384 I am bringing. Okay, that means here what to replace, no need to think. So it is fixed. So hence, since it is fixed, which block should be brought into which block of cache. So we no need to think about which block we have to replace when the cache is full. Okay. So no need of replacement algorithm in the case of direct mapping. This is the advantage. What is the disadvantage? See, at any point of time I can bring only one. Assume complete cache is free. Assume right now in this example out of 128 blocks, now only 1, 2, 3 are filled. Still 125 are still free. Out of 128, only 3 blocks are occupied. Remaining 125 blocks are free. Now assume I want to bring say 130. Block number 130. Now 130 divided by 128, remainder is what? 2. Now that means again you have to bring here only. Even though 125 blocks are free, you have to override this one only. So that is what contention. So memory contention will be there. That's the problem. That means even though so many blocks are free, we cannot store there in the free. So we need to store here only. This is the problem in direct mapping. So that means we don't have freedom. So whichever the block we want, we cannot store in anywhere we want. Okay, so even though free is not possible, this is the disadvantage. So this disadvantage of this direct mapping can be overcome in the associative mapping. In associative mapping, complete freedom is there. That means whichever the memory block we can place in any of the cache block. There is no formula. Okay, there is no formula. This one, there is no formula. Okay, there is no formula. What we are using in what? In direct mapping. Okay, there is no such formula. You can place any block of the main memory into any free block of the cache. Wherever, see, I'm only 3 filled. Now 384, that is 0. Next, I want to bring 128. You bring wherever it is free, you bring out that 128 here. Not a problem. Suppose if this is free, 128, I will bring. So this is free, 128 bring. So this is bring belong to group number 1. So this is tag is 1. Okay, so that will be say some number, whatever this block number. It doesn't matter. It may be X, whatever. That means here there is no such restriction like direct mapping. Any block of the main memory we can brought into any of the free cache block. That's it. Very simple. Since I don't want tag here in the associative map, there is no concept of tag. Okay, because I can fill anywhere if it is free. But what is the problem? So earlier I'm searching only the 5-bit tag. Because tag was there in the direct mapping, I can search only 5. Since there is no tag, here 16-bit address we are dividing into 16-bit address. Anyone for word we need 4 for word. So remaining out of 16, 16 minus 4 is 12. Remaining complete 12 we are used to identify the cache block. So a complete cache block, this block number only take 12 bits. So complete this 12 bits used to for identify the cache block only. So remaining 4 bits used to identify the word. So only this one. That means instead of searching 5 bit means 32. In 32 group I am searching. Instead of that, 2 to the power of 12, 12k, 2k. 2 to the power of 12 is 2k. 202. 2 to the power of 12 is equal to 2048. That means this much I need to search. This method, that's what? It's 128 into 16. So that is the problem. It takes too much of time. So that's what associative mapping. Okay. So hope you understood associative mapping. Now, what is the disadvantage of this associative mapping? It takes too much of time. Okay, but what is the advantage? So we can have complete freedom. Whichever the block we can store, wherever it is free, we can store there. That is the advantage. Okay. So now, so to overcome the disadvantage of this associative mapping, so we go for one more mapping called set-associative mapping. In the set-associative mapping, what we are doing, so whatever we are using this here, okay, this is tag again, we are using tag. Okay, so now I am grouping, these blocks into sets. Okay, these are individual blocks till now we discussed. Now the blocks I will group as a set. I make as a pair or group. Now I will say these two I will make it as 2. Okay, in one set. So this is say set 0. Similarly, this is set 1. This similarly the last one. Okay, this is what set. So totally how many blocks? 128 blocks. 128 blocks I am making group of 2. Okay, totally how many groups are get? 64 sets. So 64 means last 0, 1, 2, last is 63. Set 63. Okay, so totally I am having 64 because 128 divided by 2, 64. So 0, I am having 64 set. 64 set. Now the address is now I am dividing like this now. Again 4 bits. For what? Word, to identify the word. Another next block. How many blocks are there here? Now, how many sets? Totally 64. Now I am identifying set. Which set? So 64. 64. 2 to the power of what is equal to 64? 2 to the power of 6 is equal to 64. That means 6 bit to identify which set. Okay, now out of 16 bit, 10 bit over, remaining 6 is for block. Cache block. Okay, this block we are using only for 6 bits. Now, what is the advantage? Now, assume whenever I want to move any of the main memory block, I will move to any one of the sets. Again, sets. Suppose if I bring this sets, now assume, now 128 I want to move. Where to move? 128 into 0. So 0, but already 384 is in 0. But in this set, one more is free. So you move 128 here. Like that. So that means you can have more. Fact, if any one set, one block is occupied, so in another block of the same set we can store. So it is easy for identifying. Instead of searching in 128, I am searching only 64. Similarly, in order to reduce much time for the search, instead of making set of 2, we can make set of 4, 4. If you make set of 4, 4, then how many set will get? Only 16 set. 16 set. 16 set means set 0, set 1 up to 64. That means now suppose this is your cache. 1, 2, 3, 4, 1, 2, 3, 4. So now this 1, 2, 3, 4. This is my set 0. Next 1, 2, 3, 4. Now this is my set 1. Similarly 1, 2, 3, 4. This is my set 15. So now total is 16 set. 16 is going to what? 16 is going to 2 to the power of 4. That means only 4 bit. At that time only 4. 4 plus 4, 8. I need adjustment 8. Now this is the address. Right. So this is 16-bit address. We are dividing like this. If we decided in one set 4 blocks. Okay, this got 4 set associative. If you decided only 2 blocks in a set, 2 set associative. Like that, you can have any number of blocks in one set. So that will call as a K set associative mapping. Okay, if you make all 128 is one group, it's not fully associative. So exactly that's as associative. But if you make it in one set, only one block, it is nothing but direct mapping. So this set associative mapping utilizes the advantage of direct mapping and as well as what? Associative mapping. So this is what the K set associative. So this concept of mapping functions will be understood. See, initially you may feel difficult, but after writing, so you watch once or twice and you take some examples and you do that, definitely you will understand. So just a practice. If you practice for 1 or 2 examples, definitely you will understand. So hope if you people understand. Suppose if you have any questions, please write it in the comments. Thank you. Thanks for watching.